Okay, so when you really think about the basic ingredients for life, what's the very first thing that pops into your head? Yeah, for pretty much all of us, it's a star, right? The warmth, the light of a sun. It's our most fundamental assumption. But what if it's completely wrong? Today, we're going to dig into a really radical idea that life might not need a star at all.
So let's just jump right in with the question that could change everything we think we know. Is a star an absolute non-negotiable requirement for life? For decades, the scientific consensus on that was a pretty firm yes.
I mean, this whole idea was formally laid out way back in 1959. We call it the Goldilocks zone. It's that perfect little strip of real estate around a star where it's not too hot, not too cold, but just right for liquid water to exist on a planet's surface. And for a long time, this was the absolute foundation of our search for life out there. But a new discovery is forcing us to rethink that entire playbook. It turns out our galaxy might have a massive, hidden population of planets that just don't play by these rules because they don't even have a star to orbit in the first place.
So, say hello to the rogue planets. These things are basically cosmic orphans. They're worlds that were born inside a solar system just like ours, but at some point they were gravitationally booted out, ejected, to wander the cold, dark emptiness of interstellar space all by themselves. Imagine that. No sunrises, no sunsets, just endless darkness.
And here's the part that's going to absolutely blow your mind. They are not rare, not at all. In fact, our best estimates right now suggest that these rogue planets might actually outnumber all the other planets that are nicely orbiting stars in our galaxy. We could be talking about hundreds of billions of them in the Milky Way alone.
So this really lays out the fundamental difference, right? You've got a world like Earth, which gets its energy from an external source, our sun. That's what makes our surface habitable. But a rogue world? It has to rely on its own internal heat, deep down in its core. And that means any potential life wouldn't be on some brightly lit surface, but deep below, in a huge, completely dark subsurface ocean.
So how in the world could a planet just floating out there in near absolute zero space possibly stay warm enough for liquid water? Well, it needs its own engine. It needs a furnace deep inside its core.
And it turns out there are two main ways it gets that heat. First up is radiogenic heating. This is basically just the energy that's released from the slow, steady decay of radioactive elements like uranium and thorium down in the planet's mantle and core. And second, you've got all that leftover heat from the planet's violent birth billions of years ago. You put those two together, and they can actually generate a surprising amount of energy.
And this is the recipe for a habitable rogue world. An Earth-sized planet's core can pump out something like 20 to 25 terawatts of power. That's an enormous amount of energy. This heat constantly seeps up, warming a global ocean from the bottom. And here's the crucial part. A super thick ice shell, we're talking maybe 5 to 30 kilometers thick, acts like the perfect winter coat, insulating that liquid ocean from the unbelievable cold of outer space.
Okay, so we've got heat, we've got liquid water. That's two of the big three ingredients for life. But what about energy? I mean, without sunlight for photosynthesis, what could possibly power an entire biosphere?
Well, the answer is chemistry, something called chemical disequilibrium. Now that's just a fancy way of saying you have this powerful mixing of different chemicals, some that want to give up electrons and some that want to take them. Think of it just like the positive and negative terminals on a battery. Little microbes can actually tap into that energy gradient to power their metabolism. It's a process we call chemosynthesis, and it completely replaces the need for sunlight.
And these worlds have all the tools they need to build this kind of battery. You've got processes like serpentinization, where hot water reacts with rock on the seafloor, producing energy-rich hydrogen gas. Then, at the same time, radiation from the core can literally split water molecules apart, creating oxidants like oxygen. And where do all these delicious ingredients mix and mingle? At hydrothermal vents. They become these hotspots of chemical energy, these power stations for any potential microbial life.
This all sounds great in theory, but there's a really critical question, isn't there? How long could these conditions actually last? Is this just a fleeting moment in a planet's life, or could this habitable window stay open long enough for life to, actually get started and evolve?
And the answer is just incredible. Our best models predict that a rogue planet's internal heat can keep a liquid ocean going for 2 to 4 billion years. Let that sink in. That's a time frame that's totally comparable to the habitable window we've had right here on Earth. That's more than enough time for life to potentially get going.
So look, the main takeaway here is this. For every single requirement for life as we know it, these rogue planets offer a completely different, yet totally plausible solution. Instead of a star to get liquid water, they use their own geothermal heat. Instead of sunlight for energy, they use chemistry, those redox gradients. And instead of a stable orbit for long-term stability, they use that thick, insulating ice shell.
And when you put all of that together, you arrive at a conclusion that is, well, it's staggering. If these worlds can host life, and if they really do outnumber planets like ours, it could mean that most of the habitable places in our galaxy are actually these dark, starless worlds.
The implications here are just enormous. This completely rewrites the strategy for finding life out there. We can't just look in the Goldilocks zone anymore. We're going to need new methods, like powerful infrared telescopes that can hunt for the faint traces of heat leaking out of these ice-covered oceans. It even gives us a whole new way to think about the Fermi paradox. Where is everybody? Well, maybe the galaxy seems so quiet because most of the life isn't out in the open. Maybe it's thriving deep beneath the ice, in total silence.
As one of our sources put it so perfectly, this theory suggests that the galaxy may be filled with silent, sunless biospheres, hidden in plain darkness. It's an idea that's both incredibly exciting and, honestly, a little haunting. Which, of course, leaves us with one last, really big question to think about. If the most common places for life in the cosmos aren't warm, sunlit worlds like Earth, but are instead cold, dark ocean worlds hiding out there in the interstellar night, how on earth are we ever going to find it?